Germany, February 20th, 1944. Big Week, Air Offensive. At 25,000 feet over Leipzig, waist gunners of the 305th Bomb Group fought not only Luftwaffe interceptors but a temperature of -45 degrees Celsius. Oxygen masks froze to faces. Metal gun triggers bonded to bare skin. In one mission, 41 men of the 303rd Group returned with frostbite. 6 required amputations. At these altitudes, exposed flesh could freeze in 90 seconds. Commanders had prioritized altitude for safety, believing it offered protection from flak. The opposite proved true. The higher the bombers flew, the greater the human toll. Within months, the United States Army Air Forces introduced electrically heated flight suits and gloves powered directly from the B-17's generator. Frostbite casualties fell by over 90%. It was not a new weapon but wiring, a technical adaptation that saved thousands of men in a war defined by machinery. Washington, D.C., 1939, Wright Field, Ohio. On an evaluation board table at Wright Field, a B-17 test report lists fuel, oxygen, and high-altitude performance parameters above 30,000 feet. Officers from the Air Corps Tactical School Review predicted bombing accuracy and survivability curves. The men wear pressed uniforms. The room smells of fresh mimeograph ink. Outside, a prototype B-17B climbs into clear skies, its engines drumming steadily as it reaches altitude no bomber had sustained before. Doctrine assumed high altitude would minimize losses. Early staff estimates projected approximately 1% casualty per mission for tight, well-escorted formations. The mathematics looked solid. The engineering reports confirmed oxygen supply and structural integrity. But the calculations missed one variable. The human body was exposed to stratospheric cold for hours at a time. Combat data from 1942 through 1943 would contradict the medical assumptions embedded in those projections. Air Corps Tactical School instructors and Material Division officers at Wright Field formalized high-altitude precision doctrine in pre-war memoranda. They studied German tactics. They reviewed British experience. They calculated fuel loads and defensive armament. But none of the planning documents addressed sustained physiological stress at -40 degrees Celsius. The B-17B, B-17C, and B-17D underwent test climbs. Engineers evaluated oxygen regulators. Quartermasters specified early unheated leather and sheepskin clothing in supply tables. The gear looked appropriate. It met peacetime standards. But peacetime standards assumed short exposures, not 6-hour missions deep into enemy territory. By March 1943, United States Army Air Forces Medical Service Bulletin No. 21 summarized an emergent problem. Cold injury incidents among flight personnel now constitutes a major cause of non-battle attrition. The language was clinical. The reality was brutal. Men were losing fingers, toes, and noses to frostbite faster than to enemy fire. Pushing ceilings into the stratosphere increased exposure time in severe cold, an unpriced cost in the original doctrine. The altitude that promised safety imposed a physiological casualty rate greater than some raids' flak totals. Wright Field had built a bomber that could fly higher than any before it. But the human crew could not survive the environment the aircraft created. Royal Air Force Bassingbourn, England, December 1942. Pre-dawn instrument checks in the 91st Bomb Group. Armorers pass ammunition belts, the metal links clinking in the cold darkness. The medical officer inspects oxygen fittings, his breath visible in the frigid air. Ground crew stamp their feet against the frozen tarmac. A radio operator tests his interphone, hearing only static and the distant rumble of engines warming up. Air crews expected enemy fighters and 88mm flak. Those threats filled the briefings. Intelligence officers pointed to reconnaissance photographs showing gun emplacements. Combat reports detailed Messerschmitt tactics. But the crews encountered something the briefings never mentioned. Frozen oxygen lines, congealed lubricants, and numb hands unable to cycle a charging handle. Lieutenant Colonel Harry G. Armstrong at the Aero Medical Laboratory at Wright Field circulated thresholds for cold injury. Group surgeons in East Anglia forwarded case counts. The numbers climbed weekly. After one mission over Lille, the 91st Bomb Group logged 14 frostbite cases. After a raid on Saint-Nazaire, the number reached 23. The pattern was unmistakable. Unheated tail and waste stations in the B-17F became torture chambers at altitude. The A-10 oxygen regulators functioned, but moisture in the lines froze, blocking airflow. A-2 leather jackets and sheepskin suits provided insulation, but no active warmth. Silk and wool layering helped, but only for the first hour. After that, the cold penetrated everything. The lack of active heating at gun mounts turned defensive positions into frozen prisons. Waist gunners stood exposed to slipstream. Tail gunners crouched in isolation. Ball turret gunners curled into spaces so tight they could barely move. All faced the same enemy. Temperature. Aeromedical Laboratory Report Number 178, published in 1943, documented the threshold. Injury threshold reached at approximately 2 minutes of skin exposure under representative operational conditions. 2 minutes. After that, tissue damage began. After 10 minutes, permanent injury became likely. After 20 minutes, amputation became probable. Cold-numbed fingers increased gun stoppages. Gunners couldn't clear jams. They couldn't reload ammunition belts. They couldn't adjust their sights. Reduced reaction time meant slower responses to fighter attacks. Mission aborts climbed. Manpower losses accumulated outside the enemy's intent. The Luftwaffe didn't need to shoot down every bomber. The cold was doing the work for them. By January 1943, about 1 in 12 crew injuries in some groups were cold-related, a statistic that no gunnery syllabus had prepared for. Flight surgeons filed reports. Group commanders demanded solutions. But solutions required engineering, manufacturing, and time. In the winter of 1942 through 1943, none of those were available yet. Men returned from missions with blackened fingers. Some lost sensation permanently. Others faced amputation. The surgeons did what they could. They warmed the injured slowly, knowing rapid rewarming caused more damage. They logged the cases. They sent the data to Wright Field. And they waited for an answer that hadn't yet been invented. Wright Field and Industry Liaison Offices. March through June 1943. Engineers at a Wright Field climatic chamber stitch resistance wire into prototype liners while a recorder notes skin temperature readings at simulated 25,000 feet. The chamber hums with refrigeration equipment. Technicians wear heavy coats. The test subject sits motionless, wired with thermocouples, breathing through an oxygen mask. European commanders demanded immediate relief. Cables from 8th Air Force Headquarters described the scope of the problem. Medical officers provided casualty projections. The numbers were stark. Without intervention, cold injuries would cripple operational capacity within months. American industry required design cycles, tooling, and materials allocations. The 8th Air Force asked for approximately 100,000 heated suits by summer. Production readiness allowed approximately 12,000. The gap between need and capability defined the challenge. General Electric engineers took the lead. Chief Engineer John F. Dolan directed prototype development. His team tested filament materials. Copper wire failed under vibration. Iron wire corroded. Nickel-chromium alloy proved durable. Test book entries documented each iteration. Reliable heating achieved with nickel-chromium resistance filaments. Uniformity improved in F2 pattern. The F1 and F2 assemblies used 24-volt supply from the aircraft's electrical system. A rheostat control allowed crew members to adjust heat output. Early connector failures plagued testing. Insulation frayed under repeated flexing. Engineers redesigned plug housings. They reinforced solder joints. They tested in simulated turbulence. Quartermaster procurement officers issued priority requests. The War Production Board reviewed materials allocations. Copper was scarce. Manufacturing capacity was stretched. But the medical data justified intervention. Without heated suits, the bomber offensive faced manpower collapse. Validated lab performance enabled a War Production Board priority rating. The designation AF4 placed heated suit production on the same level as aircraft engines and strategic munitions. Factories received allocation orders. Suppliers diverted materials. Assembly lines prepared tooling. Without that priority, medical attrition threatened crew availability for 1943 through 1944 operations. The arithmetic was simple. Each trained bomber crew required months of training. Each frostbite casualty removed a man from the crew pool. High casualty rates meant fewer available crews. Fewer crews meant fewer missions. Fewer missions meant slower progress toward strategic objectives. The next decisive weapon for bomber crews would be specified not by ordnance, but by the electrical section. It would carry no explosives. It would fire no rounds. But it would save more lives than armor plate. Engineers at Wright Field understood the stakes. They worked through nights. They tested every variable. They built something that had never existed before. A garment that could keep a man warm at the edge of space. The prototype suits went to England in July 1943. Limited quantities meant limited deployment. Only priority crews received them initially. But the test results were immediate. Men returned from missions with warm hands, functional weapons, and no frostbite. The proof was documented. The solution was validated. Now it needs to be mass-produced. Schweinfurt, Regensburg, Germany, August 17, 1943. Formation logs record 376 bombers airborne. Mission debrief maps filled with loss symbols. Medical officers open casualty ledgers. The raid became legendary for its losses. 60 bombers shot down, 552 men killed or missing. But another number appears in the medical summaries. 246 cold injuries among 1,728 men airborne. Altitude was supposed to reduce flak effectiveness. Instead, a large share of the day's non-fatal casualties arose from cold injuries in the unpressurized, unheated stations. The doctrine had promised safety. The reality delivered attrition from an unexpected source. Sergeant Harold Moyer's after-action remark entered the official record. "My gun jammed. My fingers wouldn't bend." His B-17 returned safely, but Moyer spent 3 weeks in hospital. His frozen fingers required slow rewarming. He lost feeling in 2 fingertips permanently. He was one of hundreds that day. 8th Bomber Command analysts compiled manpower impact tables. The 91st Bomb Group medical log showed the details. 246 cold injuries from a single day's operations. Other groups reported similar patterns. The 8th Bomber Command study estimated approximately 9% of manpower loss per mission attributable to cold. The B-17F stations most affected were the waist and tail positions. Ammunition feed belts stiffened in the cold, causing jams. Oxygen masks collected ice, blocking airflow. Lubrication viscosity exceeded operational limits, freezing gun mechanisms solid. High cold injury rates translated directly into reduced gunnery effectiveness. Gunners with numb hands couldn't track targets. They couldn't fire accurately. They couldn't clear stoppages. Subsequent escort and formation vulnerabilities increased. Fighters exploited gaps in defensive fire. More bombers fell. General Ira Eaker, commanding 8th Air Force, ordered immediate medical and equipment review. The order carried weight, a signal that altitude doctrine now required thermal engineering to survive. Eaker understood the threat. Cold was destroying his force as effectively as the Luftwaffe. Staff meetings at High Wycombe reviewed the data. Medical officers presented casualty curves. Operations officers calculated mission effectiveness degradation. Intelligence officers noted increased German fighter success against formations with reduced defensive fire. The connections were clear. The August 17th mission crystallized the problem. 60 bombers lost to enemy action dominated headlines. 246 cold injuries appeared only in classified medical reports. But to the men who flew, both threats were equally real. One killed quickly. The other disabled slowly. Both removed trained crews from the battle. Wright Field received urgent cables. The Material Command accelerated heated suit procurement. General Electric factories prepared for expanded production. Waltham Watch Company joined the program. The industrial mobilization machinery, already strained, absorbed another priority demand. The lesson of Schweinfurt was written in medical logs and casualty reports. American bombers could reach any target in Europe, but the crews could not survive the altitude without thermal protection. The solution existed in prototype form. Now it needed to become standard equipment before winter returned. Bridgeport, Connecticut, General Electric Plant, September 1943. A War Production Board clerk stamps an AF4 priority rating on procurement orders. The stamp is red ink, reserved for the highest priority war materials. A G-line supervisor signs off on the first production F2 heated assemblies. The signature commits factory capacity, materials allocation, and quality control standards. Concerns that wiring in clothing would fail under vibration led to reinforced stitch patterns and locking connectors. Early prototypes showed wire breakage at stress points. Engineers redesigned seam reinforcement. They tested flex cycles, 1,000 bends, 10,000 bends, 100,000 bends. Field breakage rates fell in successive batches. GE and Waltham Watch Company engineers collaborated on connector design. The Quartermaster Corps provided specifications. Army Air Force's medical officers supplied operational data. The collaboration merged electrical engineering, textile manufacturing, and combat medicine into a single program. The F2 design used a cotton twill shell with interlaced copper alloy filaments. The wire grid covered chest, back, arms, legs, hands, and feet. A Y cable connected the garment to aircraft sockets. Distributed heating maintained core body temperature and extremity function. Output: approximately 6.4 amperes at 24 volts. Total power consumption: 154 watts per suit. Unit cost: approximately $94. For comparison, a .50 caliber machine gun barrel cost $87. Parachute cost $62. The heated suit cost more than either, but saved more lives than both combined. Production memo from October 1943. Scale achieved at approximately 10,000 sets per month by year-end. Electrical continuity standards met with improved crimped connectors. The language was bureaucratic. The achievement was extraordinary. American industry, already producing aircraft, engines, munitions, and vehicles at unprecedented rates, added heated clothing to the output without missing a beat. Industrialization transformed a lab solution into an issue item. Scale permitted theater-wide deployment schedules before winter 1943 through 1944. Logistics officers planned distribution. Depot quartermasters prepared storage. Training officers drafted instruction manuals. The garment drew as much power as a radio set and saved more trained gunners than additional armor could. Engineers calculated weight and power consumption. Operations officers calculated mission effectiveness. The numbers justified every dollar, every watt, every ounce. Factory workers in Bridgeport and Waltham worked shifts around the clock. Women operated sewing machines. Men tested electrical continuity. Inspectors verified resistance values. Packers prepared shipments for England. Every suit carried a tag. U.S. Army Air Force's electrically heated suit. Type F2, every tag represented a man who would return from a mission with working hands. By December 1943, production reached 12,000 units monthly. By March 1944, output exceeded 20,000. By June, the goal of 30,000 monthly production was achieved. American industrial capacity, unmatched and unbreakable, delivered warmth to the coldest battlefield in history. The sky over Germany. East Anglia 305th Bomb Group, November 1943. Crew chiefs route harnesses under seats, threading the power cables through fuselage stringers. Gunners plug in and set rheostats before taxi, testing heat output on the ground. A maintenance sergeant notes breaker ratings on a clipboard, 5 amperes per station, circuit protection standard across the fleet. Fear of electrical faults under combat stress gave way to operational reports of stable performance. The initial concern was reasonable. Combining electricity, oxygen, fuel, and ammunition in a combat environment invited disaster. But the engineering proved sound. The main early failures were plug fractures and shorts at flex points, not catastrophic fires or electrical failures. 8th Air Force Surgeon's Office consolidated field reports. The 305th Bomb Group maintenance and medical sections reported joint results. Integration between maintenance crews and medical staff created feedback loops. Doctors reported injuries, mechanics traced causes, engineers implemented fixes. Breaker ratings stabilized at approximately 5 amperes per station. Mean mission duration, 6.3 hours. Cabin temperature at altitude, approximately -42 degrees Celsius. Measured skin temperature with heated suits, approximately +22 degrees Celsius. The delta, 64 degrees, represented the difference between function and failure. Failure rate reduction through improved plugs validated the iterative design process. First-generation connectors fractured under vibration. Second-generation connectors used reinforced housings. Third-generation connectors added locking collars. By November, field reliability exceeded 95%. Electrical heating has proven operationally satisfactory. The phrase appeared in the 8th Air Force Surgeon Report, December 1943. The understated language masked extraordinary achievement. Medical summary showed frostbite down from approximately 10.8 cases per 1,000 sorties in October to approximately 3.1 in December. Reliable suit function restored dexterity, decreasing gun stoppages and aborts. Gunners could load ammunition. They could clear jams. They could aim accurately. Manpower was retained for follow-on sorties instead of flowing to hospitals. Crew continuity improved. Experience accumulated. The equipment most critical to survival on some missions did not fire a single round. It generated heat, preserved human function. It enabled everything else. Without it, the best bomber in the world became a death trap. With it, crews completed missions and returned safely. Ground crews learned maintenance procedures. Electricians checked continuity before each mission. Pilots included heated suit checks in pre-flight procedures. The system became routine, integrated into operations as seamlessly as oxygen or interphone. Combat reports documented the impact. Missions that previously generated dozens of cold injuries now generated single digits. Missions that previously saw multiple aborts for cold-related crew incapacity now proceeded without incident. The statistical evidence was overwhelming. By January 1944, heated suits were standard issue across 8th Air Force heavy bomber groups. The 305th, the 306th, the 91st, the 303rd, all received full equipment sets. Distribution continued to 15th Air Force groups in Italy. The thermal protection expanded across theaters. Men who had flown missions in unheated gear understood the difference. They had felt fingers freeze. They had struggled with frozen guns. They had watched friends carried off with blackened extremities. Now they flew warm. The transformation was total. The gratitude was profound. Royal Air Force Grafton Underwood, 384th Bomb Group Maintenance. January 1944. An electrician clips a multimeter to a B-17's 24-volt bus while the auxiliary power unit hums steadily. The interphone checks clear. Crew positions report green lights. Voltage reads 24.3 volts, well within tolerance. Concerns that suits would steal power from gun turrets or radios proved unfounded. Total draw for a 10-man crew, approximately 240 watts, under 3% of generator capacity. The B-17's electrical system, designed with substantial margin, absorbed the additional load without performance degradation. The 384th Bomb Group electricians documented power distribution testing. The group communications officer noted no measurable interference on intercom circuits. Radio operators reported no static or signal degradation. Turret operators confirmed full motor function. The heated suits drew power but caused no operational problems. The B-17's 1.5 kilowatt generator output provided ample capacity. Wiring harness routing followed standard electrical code practice. Breaker panel mapping organized circuits logically. Interference testing confirmed electromagnetic compatibility. Army Air Force's Electrical Systems Memo from January 1944 documented the findings. No degraded turret or radio performance observed at full thermal gear load. The memo circulated to all heavy bomber groups. It authorized unrestricted use of heated suits without operational limitations. The marginal electrical cost yielded outsized gains in sustained crew performance. Combat effectiveness per watt exceeded any other electrical system on the aircraft. Radio equipment enabled coordination. Radar enabled navigation. Heated suits enabled human survival. All three were essential. A rare, free improvement within aircraft power budgets. Most improvements required trade-offs. More armor meant less payload. More fuel meant less ammunition. More guns meant more weight. Heated suits required only a small electrical allocation that the aircraft easily provided. In the fortress, electrons now defended crews as effectively as armor plate. The B-17 earned its nickname through structural strength and defensive armament. But thermal protection proved equally vital. Men survived flak hits and fighter attacks because they could fight back. They fought back because their hands worked. Their hands worked because of heating elements powered by the aircraft's generator. Maintenance crews took pride in the system. Electricians tested circuits meticulously. They repaired damaged wiring promptly. They maintained connector integrity. The suits became part of the aircraft as essential as engines or wings. Flight engineers monitored electrical systems during missions. Generator output, battery charge, circuit loads, all appeared on instrument panels. Heated suits registered as steady draws, predictable and manageable. Engineers learned to spot problems. A sudden load drop indicated a broken connection. A steady high draw indicated a short circuit. Troubleshooting became routine. The integration was complete. Thermal protection was no longer experimental or provisional. It was standard equipment, maintained and operated like any other system. The transformation from prototype to fleet standard took less than a year. American engineering and industrial capacity had solved a problem that threatened the entire strategic bombing campaign. London, United States Army Air Forces Medical Division, April 1944. Compiled monthly tables arrive from Theley and Kimbolton. A staff surgeon draws a declining line across a wall chart. The line starts high in October 1943 and drops sharply through winter. By March 1944, it approaches the horizontal axis. Winter projections forecast thousands more cold injuries. The predictions used historical data, previous winter casualties, projected sortie rates, expected mission durations. The curves showed exponential growth. Without intervention, cold injuries would have exceeded combat losses by spring 1944. Fielding of heated assemblies reversed the trend. The line on the wall chart told the story. October, 10.8 cases per thousand sorties. November, 7.2. December, 3.1. January, 1.9. February, 0.7. March, 0.3. 8th Air Force surgeons compiled the data theater-wide. Theater logisticians coordinated issue schedules by group and mission rate. Groups with higher operational tempo received priority deliveries. Groups preparing for intensified operations received advanced shipments. The distribution strategy maximized impact. Consolidated data showed the transformation. 1943 frostbite cases, approximately 4,066. 1944 projection under 500 with full issue. Field hospitals reported approximately 1,600 fewer admissions in second quarter 1944 versus prior winter. The numbers translated to preserved combat power. Each prevented injury kept a trained man on flight status. Each preserved crew maintained operational experience. Each avoided hospital admission freed medical resources for combat casualties. Surgeons cable to Washington. Thermal suits equivalent in value to 1,000 trained gunners. The comparison was precise. Training a gunner required 12 weeks and substantial resources. Preserving gunners through thermal protection cost a fraction and delivered immediately. Another memo. The electrically heated suit is as vital as an armor plate, The comparison honored defensive technology while recognizing thermal protection's equal importance. Both defended crews. Both enabled mission completion. Both justified their cost many times over. Lower cold injury incidents increased sortie generation. Groups maintained higher operational readiness. Fewer men on medical hold meant more complete crews available for assignment. Higher crew availability enabled higher mission frequencies. Reduced training pipeline pressure. Each prevented casualty meant one fewer replacement required. Training commands, already strained, operated more efficiently. Resources stretched further. Output increased without expanding infrastructure. The impact enabled sustained strategic raids. Operation argument in February 1944, Big Week, demonstrated the capability. Over 3,000 sorties against German aircraft production. Minimal cold injuries despite extreme altitude operations. Mission success depended on many factors. Thermal protection was one of the essential enablers. America had mass-produced not only aircraft but a thermal environment that let those aircraft be fought effectively. The phrase captured the achievement. Industrial democracy applied to human survival. Soviet forces massed armies. German forces refined tactics. American forces engineered solutions. Medical officers prepared final reports. Statisticians calculated confidence intervals. Theater surgeons drafted lessons learned documents. The documentation would inform post-war planning. It would guide future operations. It would stand as testimony to what engineering and industrial capacity could achieve when applied to human needs. Leipzig and Regensburg, Germany, February 20th through 25th, 1944. Mission schedules for Operation Argument show approximately 1,000 bombers per day. Crew issue rosters list heated gear as standard equipment. The designation means universal availability. Every crew, every position, every mission. Prior winters produced hundreds of frostbite cases. October 1942, 93 cases. November 1942, 147. December 1942, 212. January 1943, 268. February 1943, 642. The progression was relentless. During Big Week, with approximately 90% gear saturation, only 7 frostbite cases were recorded among approximately 14,495 airmen airborne. 7. From 642 to 7. The reduction was 98.9%. 8th Bomber Command operational analysts documented the outcome. Group surgeons logged the week's medical results. The contrast stunned even those who expected improvement. Heated suits had been tested, deployed, and validated. But the magnitude of success exceeded predictions. The F-2 assemblies operated at scale. Standardized breaker kits prevented electrical failures. De-icing procedures aligned with heated gloves for weapons handling. The integration was seamless. Crews operated as if thermal protection had always existed. The comparative ledger told the complete story. Prior February 1943, 642 cases. Big Week, February 1944, 7 cases. Operations notes cited approximately 6% mission efficiency gain, approximately 15% gunnery accuracy improvement from preserved dexterity. The efficiency gain reflected reduced aborts and improved crew performance. Crews completed missions instead of returning early. Bombing accuracy improved. Defensive fire remained effective throughout missions. The cumulative effect multiplied combat power. Gunnery accuracy improvement resulted from maintained hand function. Gunners tracked targets smoothly. They fired controlled bursts. They adjusted their aim precisely. Cold-induced tremors and numbness disappeared. Muscle control remained normal. The difference showed in combat film analysis. Thermal protection, though invisible on film, materially enabled the pressure campaign against the German aircraft industry. Big Week targeted Messerschmitt, Focke-Wulf, and Junkers factories. Bomb damage assessment showed substantial destruction. Production disruptions cascaded through German fighter output. But mission success required more than navigation and bombing. It required crews capable of fighting for 6, 7, 8 hours at extreme altitude. Heated suits provided that capability. They turned endurance from liability to asset. A 24-volt current supported a 1,000-bomber offensive, a ratio of means to effect few anticipated. The electrical power required to heat one suit, 154 watts. The electrical power required to heat one crew, 1,540 watts. The electrical power required to heat one formation, 50,000 watts. 50 kilowatts enabled a strategic campaign. The arithmetic was extraordinary. Industrial economies measured output in millions of horsepower, millions of tons, millions of man-hours. But sometimes victory depended on kilowatts and fingertips. Big Week proved both scales mattered. After-action reports circulated through command levels. Group commanders noted mission completion rates. Wing commanders analyzed loss statistics. Air Force commanders assessed strategic impact. At every level, the pattern was clear: thermal protection worked. Aero Medical Laboratory, Wright Field, September 1944. Survey forms from European and Mediterranean theaters are tallied on a comptometer. A statistician calculates confidence intervals on a desk calculator, the mechanical keys clicking rhythmically. The sample size is sufficient. Approximately 1,100 aircrew respondents. Comfort and performance were expected to rise modestly. Engineers predicted measurable improvements. Medical officers anticipated positive results. But measured gains were larger than projected. Aero Medical Laboratory analysts compiled standardized crew surveys. Theater flight surgeons conducted structured interviews. Questions covered thermal comfort, equipment reliability, operational impact, and subjective assessment. Responses were coded numerically for statistical analysis. Sample size: approximately 1,100 aircrew across multiple groups and theaters. Comfort rating improved from approximately 32% to approximately 87%. The delta, 55 percentage points, represented transformation from inadequate to excellent. Measured reaction time improvement at gun positions, approximately 0.3 seconds. The measurement used standardized tests, visual stimulus to trigger pull. Cold-numbed hands delayed response. Warm hands responded immediately. 0.3 of a second determined whether a fighter passed through fire or evaded it. Fewer cold-induced aborts. Mission logs documented the change. 1943, frequent returns for crew incapacity. 1944, rare returns for thermal reasons. The trend was unambiguous. Medical Research Report 239 from 1944 summarized findings. Thermal protection improved combat effectiveness equivalent to one fighter escort per group. The comparison was precise and extraordinary. A fighter escort cost millions of dollars. It required a pilot, training, fuel, maintenance, and logistics. It occupied industrial capacity. It demanded rare skilled personnel. A fighter escort provided approximately 4 hours of coverage per mission. Thermal protection cost $94 per suit. It required no pilot. It demanded no fuel beyond electrical power already available. It operated continuously for entire mission durations. It never left formation. It never ran low on ammunition. It simply kept men warm. Enhanced morale and dexterity translated to steadier gunnery, steadier bombing runs, and fewer costly early returns. The psychological impact was measurable. Crews, knowing they would stay warm, flew more aggressively. They accepted longer missions. They maintained better formation discipline. Steadier gunnery. Gun camera footage showed improved tracking. Steadier bombing runs. Bombardiers maintained sight pictures longer. Fewer early returns. Mission completion rates rose across theaters. Heat functioned as an unheralded force multiplier with effects comparable to adding fighters, at a fraction of cost and logistics. The force multiplier concept applied precisely. Military power results from combining capabilities. Adding fighters multiplies combat power. Adding thermal protection does the same. but the logistical comparison favored thermal protection overwhelmingly. Fighters required fuel convoys, spare parts, armaments, and airbases. Heated suits required only electrical power generated on board. The efficiency was unprecedented. Commanders understood the implications. Equipment that improved combat effectiveness without demanding scarce resources represented ideal solutions. Heated suits checked every box. Effective, affordable, sustainable, scalable. The September 1944 report became reference material for post-war planning. It documented not only immediate impact but principles for future applications. Thermal protection in jet aircraft. Pressure suits for high-altitude reconnaissance. Life support for spacecraft. The lineage would extend decades. War Production Board, Detroit and Northeastern suppliers. March through May 1945. A procurement officer signs a delivery acceptance form. The fountain pen scratching across official paperwork. A factory worker crimps connectors onto glove elements, the copper wire reclaimed from civilian radio equipment. Inspectors verify resistance values with ohm meters. Packers prepare crates for Atlantic shipment. Concerns about material scarcity proved manageable through reclamation. Copper was precious. Military and civilian demand exceeded mining output. Recycling programs mobilized nationwide. Citizens turned in cookware, wiring, and plumbing. Industry reclaimed scrap. The supply chain adapted. Output expanded as air operations peaked. Monthly production reached 30,000 sets by March 1945. The rate sustained through war's end. Cumulative output approached 1.2 million components. Suits, gloves, boots, and accessories. War Production Board administrators coordinated allocation. Plant foremen scheduled shifts. Army, Navy Munitions Board liaisons verified delivery schedules. The bureaucratic machinery, complex and vast, functioned with increasing efficiency as war progressed. The F-3B evolution incorporated field feedback. Improved connectors reduced failure rates further. Revised heating element distribution optimized warmth patterns. Lighter materials reduced weight without sacrificing performance. Each iteration improved on predecessors. Cross-service adoption extended thermal protection beyond bombers. Naval aviation received suits for patrol aircraft operating over the North Atlantic and North Pacific. Aircrews in PBY Catalinas and PB-4Y privateers faced similar cold exposure. Army Air Force's transport crews received suits for high-altitude cargo operations over Himalayan routes. Flying the hump. Armored forces experimented with heated clothing for tank crews in European winter operations. Results were promising but limited by vehicle electrical capacity. Post-war development would address those limitations. Total issued components by VE Day, approximately 1.2 million pieces. Monthly rate, approximately 30,000 sets. Program cost, approximately $17 million. Estimated manpower recovery value, approximately $45 million. The cost-benefit analysis was straightforward. $17 million invested, $45 million returned. The return on investment, 265%, exceeded most war programs. Few acquisitions delivered comparable value. Manpower recovery included preventing injuries, reduced hospital stays, maintained operational readiness, and avoided training replacement cycles. Each category contributed measurable savings. Aggregated, the benefits overwhelmed costs. War Production Board status sheet noted, AF4 priority maintained. Copper reclamation offsets new draw requirements. The notation confirmed sustained industrial commitment. Priorities established in 1943 held through war's end. Material constraints never limited production. Scaling ensured sustained protection into 1945 operations and seeded post-war thermal gear baselines. Engineers documented design specifications. Manufacturing processes were standardized. Quality control procedures were refined. The knowledge base would inform future development. Factories prepared for reconversion to peacetime production. But thermal protection technology would not disappear. Military planning recognized continuing need. High-altitude flight was permanent. Cold exposure remained constant. Solutions validated in war would serve in peace. In a war measured in tons of bombs and barrels of fuel, a few pounds of wire quietly protected the crews who delivered both. The phrase captured the paradox. Massive industrial output supported by small but essential components. Liberty ships carried supplies. B-24s dropped explosives. Heated suits kept men alive to operate both. Factory workers who assembled suits rarely saw the results of their labor. They crimped connectors in Detroit. They stitched shells in Bridgeport. They tested circuits in Waltham. But thousands of miles away, men flew missions and returned safely because of that work. Letters from airmen occasionally reached factories. "Thank you for the heated suit. It saved my hands," simple words. Profound gratitude. Factory bulletin boards displayed such letters. Workers read them during lunch breaks. The connection between the production line and combat crew became tangible. By May 1945, the program was mature, proven, and indispensable. V-Day brought an operational pause in Europe. But Pacific operations continued. B-29s over Japan flew at similar altitudes. Heated suits deployed to Marianas bases. The technology transferred seamlessly across theaters. The industrial achievement matched combat achievement. American factories had produced 50,000 aircraft in 1944 alone. They had produced millions of shells, thousands of tanks, countless vehicles. Adding heated suits to that output demonstrated depth of capacity. No bottleneck constrained it. No shortage prevented it. Industrial democracy delivered everything required. 8th Air Force Headquarters, London, December 1945. Final medical summaries are bound in leather covers. The cover sheet lists theater totals for battle and non-battle injuries. A clerk types the final entry. A surgeon reviews the numbers one last time. An officer signs the approval line. Early war winters suggested chronic cold attrition. October 1942 through February 1943, 2,837 frostbite cases. The projection for 1943 through 1944, without intervention, exceeded 6,000 cases. The projection proved unnecessary. The final ledger shows a reversal. 1943 frostbite, approximately 4,066 cases. 1944, approximately 412. 1945, approximately 93. A cumulative decline of approximately 97.7%. Theater surgeons' office analysts tabulated outcomes across groups, wings, and air divisions. Demobilization staff summarized disability outcomes for pension and medical boards. The documentation would serve veterans for decades. Heated assemblies became standard across cold weather operations worldwide. European theater, Mediterranean theater, Pacific theater, all incorporated thermal protection into equipment tables. The innovation transcended its origin. Discharge records showed approximately 2,500 airmen spared amputation or permanent disability compared with pre-issue trends. The number represented men who returned to families intact. Men who worked post-war jobs with full function. Men whose lives were not defined by injury. Statistical projections based on 1942 and 1943 casualty rates predicted over 7,000 amputations or permanent disabilities through war's end. Actual outcome, under 500. The difference, 2,500 men, represented the program's human measure. Surgeon General's report from 1946 summarized, "Thermal gear preserved the efficiency of the air forces at a critical juncture. The language was restrained. The achievement was monumental." Critical juncture. Late 1943 through early 1944. Period when strategic bombing transitioned from experimental to decisive. Period when crew losses threatened operational sustainability. Period when cold injuries rivaled combat losses. Reduced medical attrition sustained sortie rates. Groups maintained a higher operational tempo. Experienced crews accumulated mission counts. Replacement demand decreased. The training pipeline operated within capacity. Stabilized experience levels on crews improved mission effectiveness. Veteran crews navigated better. They bombed more accurately. They defended more effectively. They survived more frequently. Experience compounded across missions. Lowered replacement pressure on training commands freed resources for expansion. New groups formed more easily. Existing groups maintained strength more reliably. The strategic effect rippled through organizational levels. The numbers closed like a balance sheet. A small electrical draw returned entire crews to operations who would otherwise have been lost to the cold. The accounting metaphor suited the outcome. Debits and credits. Inputs and outputs. Cost and value. Input, electrical power, approximately 150 watts per man. Output, preserved combat capability worth thousands of training hours and millions of dollars. Return on investment, incalculable by normal metrics, but demonstrated in every completed mission. The final medical report went into archives. Copies distributed to Air Force Historical Division, Surgeon General's Office, and Material Command. The documentation would inform future research. It would guide post-war equipment development. It would stand as evidence of what engineering could achieve when directed toward human preservation. United States, 1946 through 1969. United States Air Force and NASA Research Divisions. A post-war engineering review compares flight suit heating elements with emerging aerospace life support requirements. Engineers examine wartime equipment alongside new jet aircraft specifications. The connection is immediate. Resistive heating principles remain valid regardless of platform. Heated clothing was created as a wartime expedient. It became a baseline for jet-era anti-exposure suits and spaceflight thermal control. What began as a solution for B-17 gunners evolved into a foundation for high-altitude flight and space exploration. United States Air Force human factors engineers studied thermal protection across aircraft types. Jets flew higher and faster than propeller aircraft. Cockpit pressurization helped, but failures still exposed crews to extreme cold. Heated suits provided backup protection. NASA systems integrators adapted resistive heating principles to pressure garments. Mercury program spacesuits incorporated electrical heating in gloves and boots. Gemini suits expanded coverage. Apollo suits integrated thermal control into life support loops. Evolution proceeded from cloth-integrated resistive grids to modular liners. Wartime suits embedded wires directly in fabric. Post-war designs used removable heating layers that could be replaced or upgraded independently. Modularity improved maintainability. Thermal regulation tied to pressure suit life support loops in Mercury and Apollo. Space suits required heating and cooling. Heating in shadow, cooling in sunlight. Active thermal management became as vital as oxygen supply. The United States Army Air Force's technical report from 1947 documented the achievement. Between 1943 and 1945, frostbite casualties declined by more than 90%. Not through new weapons, but through better wiring. Better wiring. The phrase understated revolutionary impact. Wiring represented electrical engineering, materials science, manufacturing expertise, and systems integration. Wiring represented industrial capacity and organizational will. Wiring represented recognizing problems and solving them. A solution created to keep gunners' fingers functional at -45°C became a core principle of human survival in high-altitude and vacuum environments. The lineage was direct. B-17 waist gunners in 1943 to Apollo astronauts in 1969. Same challenge, evolved solution. From unheated gun positions to spacecraft, the through line was identical. Victory and survival depended on engineering the human environment as carefully as the machine. Aircraft engineers designed airframes, engines, and systems. Life support engineers designed the environment for humans operating those systems. Both were essential. The principle extended beyond aviation. Arctic exploration, high-altitude mountaineering, deep-sea diving, all benefited from electrically heated clothing technology. Commercial applications followed military development. Outdoor workers, utility crews, and emergency responders used descendants of wartime designs. Patents filed during the war entered public domain afterward. Technology transferred to civilian sector. Companies produced heated jackets, gloves, and boots for consumer markets. The innovation that saved bomber crews eventually warmed hunters, skiers, and motorcyclists. But the origin remained military. The urgent need, vast resources, and engineering talent that war mobilized created solutions peacetime might have delayed. Heated suits demonstrated what focused effort could achieve. The lesson transcended specific technology. The high-altitude bombing campaign revealed a hidden attrition driver, cold. Altitude that promised safety from flak imposed physiological casualties commanders hadn't anticipated. Men flew missions and returned with blackened fingers, damaged tissue, and disabled hands. The casualties weren't inflicted by enemy action. They resulted from the environment. Electrically heated suits converted aircraft power into human endurance. The principle was simple: resistance heating. Current through wire generated warmth. Wire woven into fabric distributes warmth to body and extremities. Rheostat control allowed adjustment. Connection to the aircraft electrical system provided power. The implementation required engineering, manufacturing, and logistics at scale. Prototype development at Wright Field. Industrial mobilization through General Electric and Waltham Watch Company. War Production Board priority allocation. Theater-wide distribution through 8th Air Force and 15th Air Force. Training for maintenance crews. Integration into operational procedures. The outcome justified every effort. Frostbite casualties were cut by over 90%. 4,066 cases in 1943. 412 in 1944. 93 in 1945. The decline was 97.7%. Improved gunnery accuracy resulted from preserved dexterity. Gunners with warm hands tracked targets. They fired accurately. They cleared jams. They maintained defensive fire throughout missions. The difference showed in combat results. Reduced aborts from crew incapacity increased mission completion rates. Crews that previously returned early for cold injuries now completed assignments. The sortie generation rose. Operational tempo increased. Strategic pressure intensified. Sustained sortie rates at decisive moments enabled campaigns that might otherwise have faltered. Operation Argument Big Week in February 1944 demonstrated the capability. 1,000 bombers daily over Germany. Minimal cold casualties despite extreme operations. Mission success depended on many factors. Thermal protection was essential among them. This was logistics and human factors engineering at scale, executed through priorities, procurement, and manufacturing. War Production Board allocated materials. Factories produced equipment. Depots distributed supplies. Maintenance crews installed and serviced systems. Medical officers monitored outcomes. The organizational achievement matched the technical achievement. The outcome was measured not in weapon lethality but in preserved hands, preserved crews, and completed missions. No gun fired more accurately because of heated suits. But gunners fired accurately because their hands worked. No bomb fell harder because of thermal protection. But bombs fell on target because bombardiers maintained steady aim. Preserved hands meant men who returned home whole. Preserved crews meant intact teams with accumulated experience. Completed missions meant strategic objectives achieved. The measures were human, operational, and strategic simultaneously. American industrial democracy demonstrated capability to solve problems through engineering and manufacturing. The solution wasn't more armor or more guns. It was better understanding of human needs and better application of available resources. Electrical power existed on aircraft. Human cold exposure existed at altitude. Engineering connected the two. The program cost $17 million. The value in preserved manpower exceeded $45 million. But the true value transcended accounting. Men who might have died. Men who might have been disabled. Families remained intact. The nation preserved its trained personnel. Post-war development extended the technology. Jet-era flight suits. Space suits, Arctic gear. The principle remained constant. Active thermal control enables human function in hostile environments. From B-17 gun positions to the lunar surface, the lineage was direct. The electrically heated flight suit never appeared in wartime propaganda films. It generated no dramatic newsreel footage. It won no battles visibly, but it quietly reshaped air combat efficiency. It proved that survival and victory could depend not on weapons but on understanding the human machine. Engineers at Wright Field understood humans as systems. Crews required oxygen, pressure, temperature, and protection. Altitude provided tactical advantage but imposed physiological cost. The solution balanced both. Fly high, stay warm. Simple in concept, difficult in execution, essential for victory. The men who flew at 25,000 feet over Germany fought two enemies: Luftwaffe fighters and physics itself. Heated suits defeated the second enemy. That victory enabled fighting the first effectively. The combination determined outcomes. In the final accounting, the strategic bombing campaign succeeded through many factors: aircraft production, crew training, tactical innovation, and logistical support. Among those factors, thermal protection occupied an essential but unheralded position. It wasn't glamorous. It wasn't dramatic, but it worked. The lesson extended beyond World War II. Military effectiveness depends on sustaining human performance in demanding environments. Technology that enables humans to function enables mission success. Investment in life support returns dividends in combat power. Today, descendants of those wartime heated suits serve in multiple domains: military aircraft, spacecraft, Arctic operations, underwater work, and civilian applications all use electrically heated clothing. The technology matured from wartime expedient to permanent capability. The men who flew without thermal protection in early war years earned respect for enduring what should have been unendurable. The men who engineered, manufactured, and fielded thermal protection earned recognition for solving what seemed unsolvable. Together, they demonstrated what free people united in common cause could achieve. From factory floors in Bridgeport and Waltham to frozen gun positions over Leipzig, from Wright Field Laboratories to 8th Air Force Headquarters in London, the program connected thousands of individuals in shared purpose. Their collective effort saved thousands of lives. The B-17 earned its name, Flying Fortress, through structural strength and defensive armament. But its greatest protection came from something simpler: wire, current, and warmth. The combination kept crews alive, missions effective, and strategic pressure sustained. Victory in the air war over Europe depended on many elements. Among them, a $94 suit powered by 24 volts occupied an essential place. The equation was stark. Without thermal protection, crews froze. With it, they fought. The difference determined history. If you value fact-based history grounded in verified archives and numbers, consider supporting research that preserves these stories. Every technical document, every medical report, every production memo represents decisions that changed lives. Understanding how engineering and industrial capacity solved human problems honors both the men who flew and the people who supported them. What is your perspective on this part of history? Share your thoughts in the comments, because every memory and reflection helps keep the past alive.